AP Chemistry, Molecular Geometry, the VSEPR Model. Specifically, what we're going to look at today is limitations of Lewis dot structures, bond angles, bonding versus non-bonding pairs of electrons, electron domain geometry, molecular domain geometry, and finally, non-bonding electrons and multiple bonds and their effect on bond angles. Limitations of Lewis dot structures. What do Lewis structures do? They show the number and the types of bonds between atoms. They also provide a two-dimensional representation of a model. What do Lewis structures not do? Well, they don't really indicate the shape of a molecule because they are two-dimensional, and they lack a three-dimensional representation. So we can see this representation of carbon dioxide right here. It's two-dimensional, but it really does not tell us all that much about its shape. Bond angles. They're going to determine the overall shape of the molecule. Angles made by joining the nuclei of the atoms in a molecule. Along with bond length, it's going to determine the shape and size of the molecule. Common bond angles to know, very important right here. Tetrahedral in general will be 109.5 degrees, linear 180 degrees, trigonoplanar 120 degrees, octahedral 90 degrees. Then we have a situation like the shape trigonal bipyramidal. And in a molecule that has a trigonal bipyramidal shape, we have two different bond angles. We have bond angles that are in the equatorial positions, which will be 120 degrees. And we can see that 120 degree bond angle right here, 120 degrees, or back here, or in between those atoms as we see right here. The axial position will be 90 degrees. And when we talk about axial position, we're talking about a bond angle such as this, or back here, even right here. All of those are going to be 90 degrees. So two different bond angles going on in the trigonal bipyramidal shape. Most of the molecules follow an ABN formula, where N represents the number of atoms bonding to the central atom A. The shape of any particular ABN molecule can be derived from one of five basic structures: tetrahedral, linear, trigonoplanar, trigonal bipyramidal, and octahedral. Now let's talk about the VSEPR model, a model that accounts for the geometric arrangement of shared and unshared electron pairs around a central atom in terms of the repulsion between electron pairs. So a bonding pair is defined as a region in which the electrons will most likely be found, otherwise referred to as an electron domain. Non-bonding pairs, or lone pairs, is an electron domain that is located principally on one atom. An electron domain includes single bonds, multiple bonds, so double or triple bonds, or non-bonding pairs around the central atom. Let's look at two examples. The first is pH3. So if I was to draw the Lewis structure of this, I would say I have phosphorus, 1, 5 valence electrons, so 5, hydrogen, 3 of them, 1, 3, that gives me 8 electrons to work with, which is 4 pairs. So if I was to draw this out, I would put my central atom first, which is phosphorus, hydrogen coming off of each one, and I look at this and I say, okay, 1, 2, 3 bonding pairs, so I'm going to have 1 lone pair up at the top. And that basically represents 4 electron domains. So 4 electron domains in this particular molecule, if you include the bonding pairs and the non-bonding pairs. Ozone is another example. So oxygen, we have 3 of them, 6 valence electrons apiece, that's 18 electrons, which gives me 9 pairs to work with. We've worked with this particular model before because we've talked about resonance structures. So I'm going to just draw it out, and I'd say, okay, I have a central atom. I know that I'm going to have a double bond in here to an oxygen, another oxygen over here. This is going to have lone pairs around here, like so, and 2 lone pairs around here, and then 1 lone pair up here. So if I was to count up the number of electron domains here, I'd say 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electron domains. The best arrangement of a given number of electron domains is one that minimizes the repulsion among them. The shapes of different ABN molecules or ions depends on the number of electron domains surrounding the central A atom. Electron domain geometry is the arrangement of the electron domains about the central atom, including both bonding and non-bonding pairs. So in this particular model, I'd say, all right, this is a bonding pair right here, a bonding pair right here, and we would call these yellow balls right here, we'd call these non-bonding pairs. Molecular domain geometry is the arrangement of only atoms in the molecule or ion, but not the non-bonding pairs, which is why we only see the bonding pairs in this particular representation at the bottom. Steps to follow when using the VSEPR model to predict the shape of molecules or ions. Draw the Lewis structure of the molecule or ion. Count the total number of electron domains around the central atom. Determine the electron domain geometry. Determine the molecular geometry. So the example here, of course, that we have is water. And I know that the Lewis structure of water is going to be an oxygen, hydrogen, hydrogen, a lone pair up here, and a lone pair over here. So if I look at this, I'm saying to myself, okay, I have 4 domains total. If I look at the electron domain geometry, I would take into account both the bonding and non-bonding pairs. And if I do that, I would say the shape of this is tetrahedral. If I'm looking at the molecular domain geometry, I'm only looking at the bonding pairs. And if I'm only looking at the bonding pairs, I would say the shape of this is bent. So again, the electron domain geometry is going to take into account both the bonding and non-bonding pairs, while the molecular domain geometry only takes into account the bonding electron pairs. The effect of non-bonding electrons and multiple bonds on bond angles. The number of non-bonding electron pairs on the central atom distorts the ideal bond angle. The bond angle decreases as the number of non-bonding electron pairs increase. So if I was to draw 3 models of atoms, I'd say SH2. And if I quickly draw this out, I'd say SH2H is right there. 2 lone pairs, and their influence, we have these big electron clouds. And if I was to measure this, I would see that the bond angle right here is 104.5 degrees. Let's compare that to ammonia. Ammonia is a nitrogen, a hydrogen, another hydrogen, and we have a lone pair up on the top with its big electron cloud right there. And if I was to measure this particular bond angle, I'd see that, oh, it's only 107 degrees. So less lone pairs, greater the bond angle. And finally, CH4, draw this out really quickly, carbon and 4 hydrogens. And we look at the bond angle here between the hydrogens and the carbon, we see that this bond angle is 109.5 degrees. So what does this mean? The more lone pairs we have in the central atom, the smaller the bond angle. So SH2 had the smallest bond angle, while CH4, which had absolutely no lone pairs, had the largest bond angle. Here's a molecule that's linear and at 180 degrees. Once we add a lone pair, we can see that the bond angle gets smaller and is now approximately 120 degrees. If we add another lone pair, again, we see the bond angle even gets smaller and is now 109.5 degrees. Electron domains for non-bonding electron pairs exert greater repulsive forces on adjacent electron domains and tend to compress the bond angle. Multiple bonds also represent larger electron domains than single bonds, yet not as large as non-bonding pairs. So they're not going to have as much of an influence. So what did you learn? We talked about the limitations of Lewis dot structures. We talked about bond angles, bonding versus non-bonding pairs of electrons, electron domain geometry, molecular domain geometry, and then finally a little bit about non-bonding electrons and multiple bonds and bond angles. Need more help? Feel free to contact me. Have a great day.